lectures. Unfortunately, my lecturer, she got injured while walking to the lecture theater because it was raining. It's pretty unlucky. And so the latest lecture or recording was only 20 minutes long. And not only that, I cannot find another lecture, if you can tell. It should be August 11th. I should have one Wednesday, so 12th. There should be a recording for 12th, but obviously things happened. And there's nothing new except for MATLAB stuff. So yeah, sucks. So I think this time I'll be teaching This video is sponsored by Chakwa. Have you ever felt extreme loneliness? Have you rejected your humanity? Have you been thinking about VTubers lately? Then Chakwa is the solution. Before you ask yourself, what is Chakwa? You should instead be asking, how is Chakwa? Because Chakwa is. If you're in need of comfort, humanity, or a Pekka, Chakwa is. Have you butchered a word and felt embarrassed by it? Be a Chak. Do you not feel confident in teaching? Be a Chak. Be a Chak. Because Chak is. Thank you for sponsoring this video, Chak. And okay. I have this pen right here. It's a pen, and if I push it, I'm applying a force. Just pretend that it's being pushed a lot. Wow, it's doing stuff. That's cool. And what vectors are basically, okay, let's start with force. A force is a vector because it has a direction and motion. Wait, direction? It has a direction and a magnitude. So let's say that this is, this is like the top of the table, even though I'm doing it on top of a desk, which is kind of dumb, so just ignore that. So if I am applying a force horizontally, this, like so, it's moving horizontally. I should stop moving the camera. Let's try again. If I'm moving this pen horizontally, I'm applying a force horizontally this way. You see that? Wow. Which means that the direction is this way, and the magnitude, they say magnitude, but in real life, it's like saying, like, it's a fancy word for saying, like how much you have applied to it, just a number. So let's say that if I'm applying 10 newtons, force standard unit is newtons because Newton made it, and he's super smart apparently. I haven't done my research there, but basically if I'm applying 10 newtons onto this pen horizontally, then this pen is being pushed this way 10 newtons horizontally. Like, That's as easy as vectors can get. The hard part is, actually, let's get 2 pens now. Let's get 2 pens and a pencil.
Say it on camera. This is Jojo Leon.
What do you have to say about the current Hong Kong situation? Well, how can I put it? First, toxicity, right? The second, toxicity.
Louder, louder.
And third, toxicity. Yeah.
One more time.
Toxicity.
I'm gonna. Well, what do you feel about this? What do you feel about this? Oh, day 100 of quarantine. How do you feel?
Good.
But basically, I want you to know that a vector is like an arrow. It's like an arrow with some direction. It's going somewhere, and has a magnitude. It's going somewhere for how much, how long, you know. So some examples are forces. I think the easiest one is weight, and let's clear up the misconception with weight and mass, because
my body is heavy.
Why not? I think I'll do this in Paint. Boom, Paint. You have like a box. This is a box, but it's not a box. You have a box, and this is made up of like atoms, you know, like matter. And it's like, you know, it looks like this, probably. I don't know. I don't have a microscope to look at through things, you know. Wow. Yeah. So basically, this whole thing, this whole thing, this is mass. I'm trying to think of a word where I don't use, but basically it's just how many atoms, or how many, yep, it's how many. And weight is the mass of the thing under the influence of gravity. So it's like, wow, this is a force, by the way. It's a vector. Did I say that? Pretty sure I did say that. And weight equals mass times gravity. Right. And this thing is pretty similar to Newton's thing. It's F equals ma. This is an A, by the way. But in reality, we actually go a bit further than this. We want to say the sum of forces, this is sum, by the way, it's the summation thing, equals to the mass of the system times the acceleration that it's being influenced, or the influence of the acceleration. So most things, like if you have let's go back to the pen. the pen, it's on my table. This pen has some mass, it has some weight being applied to the desktop thing, and a reaction force occurs where it's pushing this pen back up, and to neutralize it. So this is a normal force. It's the normal to the table. It's normal to the table because normal means 90 degrees. See that? It's 90 degrees. So then the sum of forces in this case would equal 0, and so some examples can be seen. Some examples can be seen like trusses. Wait, no, trusses. They're pretty cool, I guess. And yeah, some other examples are water bottle on desk. Like, these images are very pretty, prettier than my footage. So let's copy this image and boom, upscale it. So actually there's a few more things. There's a reaction force, and then there's a weight force being like that, and this is equal to 0, and same here, and same here. And that's basically what we call statics. And statics is when your sum of forces when your sum of forces equals 0, because static means not moving, and calculations make it easier and stuff. And we could go a bit more in depth, like saying the moment, sum of moments is also 0. So moment is basically if it's also not like turning, because what if this water bottle was turning? I don't know, but sum of moments equals 0, and this is also torque. Doesn't matter. But what we are interested in, or what is probably a bit more interesting, although a lot harder, is dynamics. And if you can tell where this is leading, dynamics is moving stuff, and moving stuff is me throwing a pen, me throwing another pen, and me throwing a pencil, or pushing a pencil, or whatever. This is when your sum of forces, I have to do this because my physics teacher will get angry, does not equal 0, which means there's either, which means that there's some acceleration being exerted, or some acceleration in the system. So like an example is, this is my beautiful drawing of a car. It's a car. Cars move, and very fast. So there's that. So I don't know if I'm allowed to do this, but I'll do this anyway. Because I am a bad boy. Okay. And boom. Nice. It works. So bonk. Here is the thing and whatever. Can you see this? I hope so. Cool. Very nice. So yeah, we talked about that. Units. We can ignore that. Formal definition, sum dot product and cross product. This is like this is all mathy stuff, and I might go into it depending on how I feel. Notations, there's this, there's also let's use V. There's also this, and there's also squiggle, and there's also whatever. But those are not really important because I don't really do them correctly half the time. So let's get into this part. Time derivative of vector. So if you can do a bit of math, this is saying that let's whoosh and let's sketch. So basically, this is a vector. Let's say this is a vector r going in this direction with a magnitude. So let's say direction. This is okay. Let's do this. You know, we love math, right? So mm, 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 right? So let's make it a different color because I like colors. Man, I'm getting old. You know, because it used to be that I never cared about colors, but now I do. So this vector. Like once you start caring about colors, that's when you know you're old. So this has a direction of some angle, theta, right? This can be like 30 degrees, I don't know. And then it has some magnitude or some magnitude of r, right? So that's really cool. And let's introduce another vector. Let's say it's going like here. Oh shoot, I don't like that actually. Let's do this. Let's say it's going like here. And this is... Ooh, I'm getting ahead of myself. And then you would be like, wait, how do we know the direction, the magnitude stuff? And then, to answer that, well, first off, the magnitude is pretty easy. So the magnitude is still the absolute value of this vector. So if this is like 8 units, then this magnitude is 8 units. You know, if it's 8 newtons, then it's gonna be 8 newtons. You can't really change that. But the angle Like how do we get this? How do we far out? Where did my thing go? Whatever. Like how why did I write Q3? Theta question mark. How do we get this? And the answer is we need to define this thing. Ooh, bad color. We need to define this thing better. X, Y, and or the answer is it. Actually, the better answer is that it actually doesn't matter where you place your vector, because vectors are free and they're allowed to go anywhere it wants to go. So I can actually place this thing as long as this magnitude or this angle doesn't change. I can place it like here, or let's place it. Let's place it here. Yeah. See, like the angle doesn't change, or the direction doesn't change, and the magnitude doesn't change, and all is well. That's what vectors are. That's why vectors are pretty cool. You can do cool stuff with it, except they don't teach you cool stuff with it because what they want is answers, and you know, they want to know if you know. So whatever. So time derivative vector basically means that, let's say that you have I wonder if I can animate this. Oh no, it's okay. Let's say that you have a vector and like I wish I had a string, but it doesn't matter. But like you know what? Let's not have strings. I hate strings. If I can't find a string, I hate it. So basically what time is like a time. I'm gonna write this down because it's sort of important, but not really at the same time. Time is a scalar. Scalar means not a vector. And what is a vector? A vector is a magdior, and this one is number. And you can think of it as like, the buff, you know, uh, um, the buff doggo, and then, and then um, the small doggo. This is scalar, and this is vector. So that's not important. But basically, scalar means it's a number. So like it's a scale. That's why it's a scalar. That's boom, scalar. It scales up things. So when you have a vector like this, and then v, and you want to make it bigger, then you can say it's 2v now. And what's the scalar? This is the scalar part, and this is still the vector. So that's what it basically does. Not very important in terms of the whole thing, but in real life it sort of does. I don't know. I'm just a student trying to teach and failing miserably, which I'll probably edit to make it sound like I'm yeah, yep. But so you have a vector, and let's say this is going through like some time portal, and now this vector, this vector is now related to time. So if you remember the pen thing, I had a pen, I pushed it like this, I'm gonna do it here because it looks less weird. I've pushed it for like some amount of time, you know, like let's say 5 seconds, and that's what it basically means. And yeah, you know, this is a bit complicated because this has two different angles, and fundamentally, like maybe it's better that way, but so like at its first time, t initial, this vector is going this way. At t final, let's say it's going like this, right? This is v1, v2. And if we sort of connect them together magically, because vectors do be that way, it's like this, right? And then you can see that, and then if we want to know how much it moved, we can say that this part here is delta, or the change in v, right? Because, am I allowed to? Yeah, I'm allowed to do that. Yeah. This is a change in the vector, and it makes a triangle. And, derivatives, you know, maybe I should start with, fundamental calculus, which requires me to get my year 12 textbook. Fundamental theorem of calculus, recall, blah blah blah, gradient function, derivative, find, blah blah blah. So this part is important. Fx plus h minus fx over x plus h minus x, and then blah blah blah, fx plus h minus fx over h, and so on forth. So what this all means is that this applies to anything that has derivative in its thing. What this means is that, let's say you have like a graph. Oh, yeah, okay. Let's say you have a graph, and this is on some axes, x, y, and this is a function of x, or y, or, you know, y equals x squared. It really doesn't matter, but it's function of x. This is important. It's a function of x because it's on x. So if we change this to y instead of x, this is a function of y. Okay? But let's keep it simple. Function of x. You take some point. Okay, I'm actually going to go back because, you know, I'm not good. I'm not good at this. At some point, x, right? And then let's say that you take another point, x plus h, right? So then this difference here is h, right? That makes sense. And then, so then this part is function of x, right? Yeah. And this is a function of x plus h. So if we take the difference, or the gradient, you know, rise, run, because, you know, I like rise over run. This is rise, and this is run, which is equal to h. I kind of got ahead of myself there. So this is fx plus h minus fx over h, right? So this is actually the start of any derivative, or because derivative is, I'm gonna write this down. dr dt is the rate of change of r in terms of t. So essentially what this means is that you know, the rate of change, this whole gradient looking thing, it, it probably looks like some straight line like this, right? Like a very straight line from there to there. So as we, if we shrink this down to something smaller, let's say this much to this much, then we get a smaller thing, right? And then as we get smaller and smaller, this is getting smaller. This difference, h and this thing, if we decrease the difference, we get to a point where we are actually using something, what we call in math a limit, and usually it looks like this. You know, it doesn't really matter, but in this case we are decreasing the difference, or we're slowly limiting ourselves to a single point on this function fx. So what we're doing is we're changing the rate of function over dx. We're decreasing this by dx, the change of x, which is this part because it's on x. Oh, this should not be dx. It should be delta x. Very smallly, so small that when h tends to 0, this means that basically we get to a point where it's you know, we find the rate of change, or the instantaneous, or the, oops, this should be dfx over dx. We get to a point where we are just looking at the rate of change at that point. And this is important because it just is. You just use it everywhere. And I don't know why they have to introduce this theory every time. If you can see here, they do the same thing, dr dt, but it gets smaller and smaller such that there is no difference, and then now we get like a certain point. Same with this, same with velocity. And that actually just covers almost everything here. So like, just to apply this in vectors or motion, say that you're going this way, x1, x2, delta x, and then this is all over over a period of time, right? So that means that it's dx dt, as this limits t tending to 0 of this thing. Is that the right way to write it? Yeah. Yes it is. You know, this should be t. As this tends to, this is a triangle. This is also, this is a t. This is an r. We get dx dt. Oh, this should be an x, by the way. There you go. So that's what it means. We're just getting, at some point, it's like the difference is small. Like, this is so small that we're actually just like looking at a point. So this is what this definition means. And so that actually covers what's being taught this week. This, and then Cartesian, what's the time? 48. Oh, shoot. I mean, I may as well, right? So, okay. You know what? Let's just briefly go through this. Coordinate system is a math way of saying, where's your shit? Like, what is it relative to? Relative to. And to explain it, it's like saying, you know, it's like one of those lecturers where it's like, you know, they have some sort of PowerPoint slide, and then they have some bullet points, I don't know, like that. And then they, like, maybe in the actual theater, they're just like, you know, pretend this is theater and this is a desk. And then the person's just like, saying here, and there. You know those lectures if you've encountered them. But you know, here, there, and there. We all know what they're talking about if you're there, like if you were actually in the lecture theater. But my I'm a lazy person, and I don't really know half the time. I usually just watch the lecture recordings, or maybe I don't. Sometimes I don't. So all I see is this PowerPoint and some bullet points, and the lecturer just saying here and there. And, you know, we have no idea where it is anymore, and I just have to guess where it is. So that's what this really means. We want to have a coordinate system just so that anyone or everyone can tell where things are. And my phone just rang. I don't know why it did, and I'm kind of scared. But whatever. So it's just a way of saying, like, you know, you know, like you know, it's a map. It's a map, but math. It's a map, but math and stuff. And the reason why we do this is, wait, did I say that? I did say that. Okay, I'm gonna cut that part out. So this leads me to some of the ones that you don't know why the like if you remember in school, they say label your axes. Label axes. Very important. Hiya. And that's the reason why. The reason why is because we have different coordinate systems. X, Y is one of them. This is called Cartesian. From memory, this guy. What? From memory, this guy is Descartes or some person like that. Descartes. And then he was like a math person. And then he also did some philosophy, if I remember correctly. And then he was like, I think he was the first person to be like, oh, hey, we have a person. Just forget his arm. Sometimes arms can be like that. We have a person, and we also have a mind. I am mind. And he was like one of the first people. He's like, oh yeah, the mind and body are different entities. Different entities. Because why not? You know, like sometimes you can be a materialist, and you know, there's different ways of thinking how your mind body works. But essentially, he just developed this philosophy that these two are different things. They're not intertwined. Spiritualism and stuff is not a real thing, or whatever. You know. None of that, because and that's philosophy, and that's for tomorrow's lecture. So basically, he made two planes or two axes, because of that. They're called X and Y because I don't know. It could have been A B. It could have been something, but it was decided it was X Y, and that's what it is. So sometimes we also call this the real. And then actually, let's take a step back, and then we can add more axes to this. So one of the things that we can see is like X, Y, Z, or something like that, or Z. And now we have 3 axes, 3. And then we can actually add more somehow. I don't really know, but you can add as many as you want. And they say it's called n, and these are called dimensions. And n dimensions were yeah. But none of that. This is actual math stuff. I'm here to talk about real stuff and not real stuff soon. So if we define our axes like that, now we can say, okay, let's choose this color. Let's choose this color. Let's say that our vector starts at point 0, 0, 0, and it's going like somewhere here. Yeah, that looks pretty cool. And maybe it's like I don't know. 1, 2, 3. See, now that this whole and this whole thing can help make a vector and say, okay, this vector is 1, 2, 3. And just to clarify, I think it's from the origin, 1, 2, 3, or from origin. And now we can actually define where, you know, this vector is going, or, you know, where's our shit, or what's it relative to? It's relative to this axis, and that's really cool. Like, you know, even if you misplace this whole vector, let's say like here or something, we can still tell where this is because at least it's on the same axis. So like this can be like 1, 2, 3 instead, and then it's like, you know, it's 2 through 4. I don't know. It doesn't matter. But basically, now we can say, okay, this vector is going from point 1, 2, 3 on x, y, z axis. So we just take the difference, 1, 1, 1. So this axis is actually just a 1, 1, 1. It's it's uh, it's popping out like to you, like if it's like this. It's like hitting my camera right here. Yeah, that's pretty cool. So it's like a tiny thing. So there's that. What else do I need to talk about? This is coordinate system in a nutshell. For Cartesian, that is. Let's get to imaginary numbers. Imaginary numbers? No, we say polar. Polar coordinates. I don't know how much you need to know. How much should we know? Bonk. So the idea is polar coordinates are essentially another way of saying, hey, are your vectors funky? Cause I like Spelunky. I don't know. I tried to think of what rhymed, but it didn't really work. But in a way, polar coordinates, they're pretty useful in like uh, like planes, I would guess. You know? Sometimes sometimes it's not useful having just like these things saying, hey, I have like a plane going like this. Like that. This is a plane. This is a plane. Okay. And then we have like something like this. It's not really useful like for plane trajectories um or those sorts of stuff to be just saying, okay, it's going 1, 2, 3. Like at that point we were just like, what the fuck, man? Is it turning or what? Is it still like, you know? Because like at some point, like I don't know. I've only played like one of those like flash games where you know, if your plane is at an angle too big, this is a plane. If your plane is at an angle too big relative to the ground, then it's going to stall, and stalling is bad or something, you know. So in these cases, we want to use polar coordinates because then they introduce something, or not really introduce, but they talk about theta and r, which means that let's just bring this over, like, you know, and let's just use a different color this time because I'm getting lazy. Dude, shut up. What is my phone doing? I'll kill you. Whatever. So we have some vector r, and this is its angle, and so that's what this is. So now we know, like, so in this case, now we know the plane is going at some speed. Plane at r speed, and elevating at this angle theta degrees from ground. you know? And now we can be like, oh wow, this is pretty cool, and this is way better than saying, oh, uh, uh, my plane is going at 123 units from ground. I don't know, like just logically speaking, it doesn't really like this is like questionable. Like what? Like what? What? Like I don't get it. This is a certified Chakwa face. Chakwa.